Bussotti and Stamatos Papadakis. Okay?
Yes.
Okay, thank you. Each of you have 45 minutes, a little bit less for questions, of course, and the answers. So, Paolo, please begin.
Thank you. Thank you to Vincentas for this invitation, and thank you for these so pleasant days. And I am Paolo Bussotti, and I am Associated Professor at the University of Udine. Udine in the northeast of Italy, as you can see. And I spend in Udine the autumn, where I give lectures. The rest of the year I live in Livorno, that is my hometown, where I work, study and write. This is my very brief presentation. Okay, let's come to the subject of this talk. We will speak of the concept of force. Of course, I am not the intention to tell you how to teach the concept of force. This makes no sense. My intention is to give you some ideas about the possible way to approach this such a fundamental concept. And my idea is that in many cases a historical approach can be useful in order to teach the concept of modern physics. And this depends on the fact that the pupils, the students, can understand how the concepts were formed, how the concepts were born in their nascent phase. And of course this is a big help, because they are in front of the same problems, in front of which were some famous scholars, some famous physicists of the past. And of course this is a good way to approach the scientific concept. Furthermore, there is a further advantage, and this depends on the fact that through an historical approach it's also possible to understand how science was developed. And of course the development of science is a fundamental aspect for the understanding of science itself. Of course, I am not claiming that a historical approach is the best one or is the best in every case, but in some cases it can be of great help. This is my idea. And in particular, a historical approach can also teach us to distinguish two aspects which sometimes in science and in science education are joined, but that it's necessary to keep separate. And this aspect concerns the distinction between what belongs to the world and what belongs to our model of the world. Because of course science deals with the world in a mediate manner, and the mediation is given by our scientific models. Therefore, there is the world, there are the events, and there are the models through which we interpret and try to understand the events. It's not the same thing. The world is a thing. Our theory of the world is another thing. And this is true in any case, for ancient science as well as for modern science. We are working in a model of the world. In the case of physics, in a mathematical model of the world. And the history of science is of great help because it teaches us how the models of the world changed during history. But of course the world it's exactly the same. Well, with regard to the concept of force, I will start referring to the fundamentals test of classical physics, which is Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, natural philosophy at that time meant physics, written by Isaac Newton, and there were 3 editions, one written in 1687, one in 1713, and one in 1726. These editions are different from some aspects, from some important aspects, therefore it's appropriate to mention all 3 these editions. And the basic concept on which Newton constructed his physics was the concept of inertia, of which we spoke during this talk. Other scientists had some idea close to that of inertia. It's appropriate to recall Galilei, Descartes, and Huygens. But, as Einstein wrote, Newton was the first one who developed a complete system of physical causality. A complete system of physical causality. Therefore, modern physics is born with Newton. Okay? And of course, Newton was the one who introduced force by means of a complete and rigorous definition. And therefore, I will try to introduce this concept following the itinerary marked by Newton. Well, the Newtonian physics is based on 3 notions: that of mass, that of inertia, and that of force. And it's impossible to speak of the concept of force without having also dealt with the notion of mass and the notion of inertia. Since Newton gives the definitions of this concept, in my opinion, the most appropriate way to approach the teaching of physics in a classroom, and of course I am referring to students attending the 3rd or the 4th year of a lyceum, of a high school, therefore students aged between 16 and 17 years, that is the target, is the definition that Newton gave of the concept of force, of mass. Let us read what he wrote. This is the standard English translation, because the Principia were written in Latin. And what I am reading now is drawn from the standard English translation. Quantity of matter is a measure of matter that arises from its density and volume jointly. If the density of air is doubled in a space that is also doubled, there is 4 times as much as air, and there is 6 times as much if space is tripled. The case is the same for snow and powders condensed by compression or liquefaction, and also for all bodies that are condensed in various ways by any cause whatsoever. Therefore, how does Newton define mass? Newton defined mass as quantity of matter. Since he was an atomist, and since he thought that each atom was equal, of course we know that it is not the case, but he thought in this manner, the mass of a body is given by the quantity of atoms a body has. This is Newton's definition of mass. Of course, this definition can be criticized under some aspects, because it introduced the concept of density, of, okay, let us give for granted the notion of volume. It's known that it's not problematic. Anyway, the concept of density is problematic. Therefore, he defines what is known, mass, by what is still less known, that is, density. Under this respect, the definition is not perfect. But here there is a fundamental point which Newton perfectly understands, which was not understood until Newton, and that is necessary that our students understands from the beginning. The mass that is that mass is different from weight. Mass is different from weight. This is a fundamental point that, if it's not clear from the beginning, can create a lot of ambiguities, a lot of misunderstanding and confusion. Mass is an intrinsic property of an object. It depends on its quantity of matter. Whereas weight is not an intrinsic property of an object. We can say that it is a force, but it's not necessary in this moment to speak of force. It's enough to say that weight is mass by gravity acceleration. Of course, we have already spoken of acceleration, of all the kinematical quantities, therefore it's not problematic to define weight as mass by gravity acceleration. And so, whereas the mass of a body is the same everywhere in the universe, of course the weight changes according to the acceleration of gravity. For example, on Mars or on the Moon, bodies are lighter than on the Earth. On Jupiter or on Saturn, they are heavier, because gravity acceleration is bigger. This is a fundamental aspect. Well, now there is a further consideration, because Newton gives a second definition. It concerns the quantity of motion. It's defined as mass by velocity, and this is not problematic. But the third definition is the following one. He writes, inherent force of matter is the power of resisting by which everybody, as far as it is able, perseveres in its state either of resting or of moving uniformly straight forward. This force is always proportional to the body and does not differ in any way from the inertia of the mass, except in the manner in which it is conceived. And this is true, because how was conceived until now mass? It was conceived as quantity of matter, and it was connected to weight. Okay? Now mass is considered in another manner. It's considered as the possibility, as the power that the body has to change its kinetic state. It's clear what I mean? Before there is a connection with the weight, now there is a connection with the possibility to change its kinetic state. This new definition has nothing to do with weight, has nothing to do with gravity acceleration, has nothing to do with nothing. In a sense, it's an absolute definition. You have a body everywhere, you push a body, and you need some power to put this body in motion, or in contrary case, to stop this body. Okay? Good. Now, a physical quantity makes sense if we can measure this physical quantity. And how can we proceed in the case of mass, referring to this second definition of mass? How must we proceed? Well, in a very easy manner. Suppose, like in the figure, that with a trolley at rest, we impart a push to it by a machinery or through our hands. It's completely indifferent. Suppose that the road is smooth, and the trolley will start with a certain speed. It has an acceleration. It's at rest and it starts with a certain speed. Now suppose that with another trolley we have the same machine to push it, but its speed from 0 becomes 3 times that of the previous trolley. Then, based on our definition of inertial force, it's easy to understand, it's easy to extrapolate that the mass of the second trolley is 1/3 of that of the first trolley. Well, but when we have to measure the mass of a body, do we proceed in such a complicated way? Of course not. We use a balance. We know that the gravity acceleration on the Earth is 9,8 meter/second square, and we weight the body, and after that divide by 9,8. Okay, this is how we proceed. We weight a body to measure its mass. But these two concepts of mass are completely different. In one case, we measure how body reacts in respect to gravity. In the second case, we measure how a body resists to the possibility to be put in motion or to be blocked. These are two completely different concepts. In the first case, we call this concept inertial, a gravitational mass. In the second case, we call it inertial mass. How can we be sure that these two concepts coincide? How can we be sure? We cannot be sure. This is only an experimental truth. There is nothing in Newtonian theory, nothing in classical physics that, from a theoretical point of view, lets us understand that the concept of gravitational mass is the same as the concept of inertial mass. Nothing. It was only Einstein who, and not Einstein in special relativity, but Einstein in general relativity, who proved this is too much, okay, who proved that these concepts are effectively the same concept. But in classical physics, there is no guarantee, no theoretical guarantee. There is only an experimental evidence that the two concepts coincide. And of course, if this concept did not coincide, physics would be enormously more complicated, enormously more difficult, and almost impossible to be managed. But, in my opinion, it's absolutely necessary that our students understand from the beginning that these concepts, from a conceptual point of view, are not the same notions, are not the same concept. It's only an experimental truth that we can speak of mass as a sole concept, as a unique concept. Because, as a matter of fact, in our concept of mass, two different notions converge. Okay? Ernst Mach, who is a famous epistemologist, a famous historian and philosopher of science, and a famous physicist, attempted to improve the definition of mass, of Newton. As a matter of fact, he avoided the reference to density. And he wrote, all those bodies are bodies of equal mass, which, mutually acting off each other, produce in each other equal and opposite acceleration. This is exactly the same thing that I have said here, in the case of the trolley. If we produce the same acceleration with the same impulse, then the mass is the same. Okay. And from an educational point of view, it's interesting to highlight that this kind of definition is given by abstraction. What means to define a concept by abstraction? It means that the concept is not defined giving an individual definition, but it's defined by indicating when two quantities are equal with respect to that concept. It's not a traditional definition. For example, for who has a little confidence with mathematics, we can recall that Georg Cantor defined the cardinal number of a set by abstraction. He told two sets have the same cardinal number if a univocal correspondence between the element of the set exists. Okay? Thus, this kind of definition is important from an educational point of view. It is important that our student know this kind of definition. Okay, we have spoken of mass. Let us now move to the concept of inertia. It is the milestone of the whole classical physics. It's appropriate and not intuitive. As I have told, I don't repeat, Newton was the first to give a clear definition and to use inertia in his system. He defined inertia in the first law. The first law states that everybody, very famous, perceives in its state of being at rest or of moving uniformly straight forward, except insofar as it is compelled to change its state by forces impressed. As a commentary he adds, projectile perseveres in their motions, except insofar as they are retarded by the resistance of air and are impelled downwards by the force of gravity. If no air exists and if no gravity exists, when you shot a projectile, it continues along its instantaneous tangent and of course it goes far away in the skies. Okay, he also gives the example of the spinning top, but it's not necessary to repeat it here. Okay, to explain the concept of inertia to pupils, it's not necessary to have a concept of force. It's only necessary to clarify that the concept of rest is equivalent to that of uniform rectilinear motion from a cinematical and dynamical point of view. The concept of inertia precedes, from a logical point of view, that of force. Well, on the other hand, for people aged 16, 17 years, that are profoundly influenced by their practical experience, this concept is not so easy, because if you push a ball on a table, if the table is long, after a certain period, the ball will stop. The movement depends on the form, on the friction. There are many components which influence the movement. Therefore, that of inertia is an abstract concept. Another counterexample, an apparent counterexample, of course it's not, but we can say, okay, but I see that in the sky, the planets have a uniform motion. Why do they have circularly and uniformly? If there is inertia, they should go straight on a straight line. Why do they deviate from a straight line? There is no reason. No one pushes them. Why do they deviate? And not only, a particularly gifted student can ask, dear teacher, you speak of rest a uniform motion in a right line, but in respect to what do you determine these kinetic states? For me, in my car, I am at rest and the external world is moving. In the external world, I am moving. What is the situation? And of course, the first thing that must be explained is that the motion is relative. No absolute motion exists. No body is at rest or at motion in an absolute sense. Of course, we are free to choose which body to consider at rest and to construct our physics by considering that body at rest. But a state of absolute motion, of absolute rest, does not exist. On the other hand, there are some visual experience, some personal experience that can indicate this to be the direct direction. For example, when we are in a train and the train starts slowly, it seems to us that the station moves and we are at rest. And of course, the state of motion is completely relative. Now, to convince our students that the principle of inertia is a faithful, is a good principle, we could reason in this way. Consider two inclined planes without friction, like A, B, and B, C. Let's a ball to move from A to B and ask them if there is no friction. Where will come back the ball? I think that all the students will answer intuitively. It will come back at the same point, at the same A as A, in the point C as the same A as A. If two inclined planes can create some problem, we can use a half circumference, make the same thing, from A to C. Okay? And now, let's act in this way. Let's make one of the two planes always less and less inclined on the horizon. Or add, after 1/4 of circumference, a curve with a curvature with less than that of the circumference. What will happen? That the body will reach the same A as before, but in a bigger time, but this is not important. We are concentrate only on the A. And now let us make a limit reasoning. If the second plane is completely flat, and if the circumference is replaced by a straight line, what will happen? When the body will reach the place B, of course, it will continue its movement infinitely. Because it stands to reach the same height, but it can't. Because the street is now completely flat. So it will move at infinity. Of course, this is not a demonstration of the inertia principle, because it's a principle, there is no demonstration. It's only a little experiment to make it plausible. Only this. Well, and we are arrived at an important aspect, that is that inertia, the difference between our model of the universe and universe. Inertia principle belongs to our model of the universe, because in the universe there is no motion that is properly inertia, no one. But this principle, thought belonging to our theory, is fundamental to approach real movements. Therefore, it's fundamental that the students understand this principle and understand that it's not an objection to say, but in the world there is no inertial movement. Of course there is not, but inertia principle belongs to our model, and we make our inquiry on the universe through our model. We cannot make it in no other way. We need the model. It's clear? Okay. And a crucial aspect concerns the uniformity and rectilinearity of motion. Of course, in this case there is no answer. The only answer to the doubts of the students is to say that motion is relative. This is the only answer, that we cannot establish an absolute reference frame that can tell us this motion is uniform in absolute sense. This cannot exist. Okay? Therefore, if one student asks, why do you speak of uniform rectilinear motion, we can say because this is comfortable to us to refer it to some system of reference. But it's impossible to say that in absolute sense one system of reference is at rest or is moving uniformly. Okay? Now, let us see the concept of force. In the universe, not all motions, of course, are uniform and rectilinear. They are not. And therefore, it's necessary to introduce an agent which modifies the state of rectilinear motion. This agent was called by Newton force. And of course, it's possible a very pragmatic attitude, and a pragmatic attitude consists in defining simply force as my mass by acceleration. But, okay, this approach is not wrong, but it hides several interesting properties of the notion of force. In this case as well, a good idea is to follow what Newton wrote. And concerning the action of the force, he gave a definition which is the following one. Impressed force is the action exerted on a body to change its state either of resting or of moving uniformly straight forward. As most significant example of impressed force, Newton speaks of impact, pressure, of course pressure now it's not considered a force but force divided by surface, but okay, Newton spoke in this term, and centripetal force. And here there is another interesting question which connects our introduction to physical education with interdisciplinary education. Why? Well, because the origin of impact and pressure are clear, because they are forced by contact. But the general origin of a centripetal force is not clear. Let's come back to the example of the planet that move around the sun, or more easier, of an object which falls on the Earth's surface. Which force acts on this object? No one. There is no direct contact. It's free. Of course, and this is a great problem. This is a great problem, and it was a great problem in Newton's time, because, and this connects our itinerary with the teaching of history and with the teaching of philosophy, because before Newton, Descartes and also Huygens and Leibniz tried to explain every force by contact, as contact force. Is this unreasonable? Not at all. It's absolutely reasonable. And it has an historical reason. Because in the medieval period and in the Renaissance period, astrology and natural magic were developed. And such discipline claimed that had the pretension to explain many effects which takes place on the earth as due to mysterious influence of asters and celestial body which act at a distance. Descartes told, stop with these ways, this cannot work, we have to explain rationally the movement and what happens, and therefore let's move away every action at a distance, every force must be by contact. And now, the inventor of modern physics, probably the greatest genius of humanities, Newton, seems to reintroduce the action at a distance, because of course gravity is an action at a distance. No one pushes this body, no one. And of course Newton was criticized because of this. But Newton did not have the intention to come back to the old natural magic, because natural magic had no mathematical support, whereas Newton told, I don't believe that gravity acts at the distance, but I feign this and I offer a mathematical model which perfectly works to explain how bodies move under the action of gravity. This is sufficient. I don't claim to explain the origin of gravity. And of course, this is very important from an educative point of view, because in this way the pupils can understand that science is not metaphysics. Science cannot explain everything, cannot. Science has a model and explain what is within that model. If we don't know the origin of gravity, but the theory of gravity perfectly works, we have to accept this theory of gravity. And of course, to develop our research also to find the origin of gravity. But we cannot say, until I don't know the origin of gravity, I don't make physics. This makes no sense. It's clear? And therefore, this is a profound reflection. I think still 5 minutes. Okay. And therefore, this implies a profound reflection which connects in a interdisciplinary itinerary physics, mathematics, history, and philosophy. Okay. And at this point, Newton explained how a curved motion takes place. Suppose a body have a certain inertial motion. It arrives close to another body, which attracts it gravitationally, and its motion is deviated and becomes curved. Therefore, a curved motion is due to two physical properties, an inertial motion and the deviation due to a centripetal force. The composition of these two vectors gives origin, for example, to the orbital planets. Okay? And Newton gives a very clear explanation. I will leave my slides. I do not have time now to read what Newton wrote. The last definition, the eighth one, is very important because, as a matter of fact, Newton defines force by F equal mass by acceleration. He writes, the motive quantity of a centripetal force is the measure of this force that is proportional to the motion which it generates in a given time. Therefore, and this is very important, therefore, accelerative force is to motive force as velocity to motion. For quantity of motion arises from velocity and quantity of matter jointly, and motive force from accelerative force and quantity of matter jointly. This means acceleration is to motive force as velocity is to quantity of motion. Therefore, it follows that force is equal mass by acceleration. Okay? Good. And now we are ready, and I am going to conclude with this, we are ready to introduce the second law of motion. Newton said a change in motion is proportional to the motive force impressed and take place along the straight line in which that force is impressed. I want to conclude with this observation. And the observation is the following. Some scholars claim that, as a matter of fact, the second law is a definition of force. Well, this is false. Newton has already defined force. The second law is the way in which the definition is applicable to concrete physical situations. Because the second law tells us that there is a quantity which is always the same. This quantity is m mass by acceleration. In this case, using the classical Newtonian notions, we can write mass by x 2 dots. X 2 dots means second derivative with respect to time. This expression is present in every Newtonian problem. After that, each single problem has its specific forces. In the case of a pendulum, for example, we have the gravitational force, the weight force, mass by gravity acceleration, plus the tension of the thread, of course. Combining the fixed quantity of Newton's second laws, m x 2 points, with the variable quantity, the expression of force in every single problem, we can obtain the so-called equation of motion. In this case, we have an expression for the angular velocity and an expression for the tension of the thread. So we can resolve theoretically every problem. Oh, 1 minute. Of course, here we have to make some integrations, and it's possible that integrations are not possible analytically, but this is a mathematical problem, not a physical problem. There are other things to say, but my time has finished and I shut up.
Professor, you demonstrated us undoubtable fact that even heavy stuff is accessible for us if you present it as a story.
Thank you.
And you did it as a story. Thank you very much.
Thank you to you. Thank you. Thank you. Thank you, Vincentas.
Do you have questions, or it was so perfect that you don't have any questions?
No, I don't have any questions. I appreciate, basically, for me physics was a very difficult subject, let me tell you, because the teachers that time they taught in such a way, it's really complicated for us. But the way you are telling the story, actually that's why history of science is very important. And correctly you mentioned that whatever the scientific concepts that involve history, philosophy, and then another term you use, mathematics.
Mathematics.
Yeah, these things are very important, and that point I like, and I think it's not only in physics but also in biological sciences also.
I think so.
Yeah,
I think
and
so
all
as
sciences.
well.
Thank you.
Thank you.
Thank you very much.
Okay.